Welcome, everyone. I really hope you had a great break. We'll continue with imitation learning, and we'll enter into model-based RL today. That's very exciting. We're going to have many lectures on model-based reinforcement learning. I think today homework 2 is due. Now, I don't know if the break created some problems on TX getting back to you and so on for your questions. We'll see if there are too many problems. We'll discuss with my TAs or Roshan and Josh, and we'll see what we can do about this. Okay, I haven't been able to talk to him about this. Now, today mid-semester grades are due, so we're going to give you some grades. These grades are very preliminary, simply because we're encouraged to show these mid-semester grades. It's going to be based on quiz 1 and homework 1. Okay, we know that we have 5 homeworks and 3 quizzes, so it's not going to be super indicative of what's going on, but you will also know the cutoffs, I think we published and so on Piazza, etc. Yeah, so if you have any other questions, please see me on the office hours after class, okay? So last time we started talking about something really, really exciting, which was imitation learning for manipulation. And specifically, we discussed transporter networks, if you remember, that were able to, perform a variety of tasks in a tabletop environment, okay? And I remember you guys suggested some obvious things, how the network should be parameterized to predict peak and place locations. And then somehow the actual architecture, right, of transporter networks came as a surprise. Potentially, it was not like super intuitive of what to do. For example, many of you wanted to predict directly from the image and 3D robot gripper, okay? And the problem with this is that if the computer or the laptop that you're trying to close or to pick up or the mug and so on moves a little bit, that 3D gripper location changes, okay? And if your goal is, if your architecture, the way you wired the network is to take a whole image, condense it into one vector to spit out and to regress to that 3D location, then this network is not equivariant under translation and rotations of the objects in the scene. So equivariance is what we're looking at, all right? This is what we're after. Why convolutions are equivariant? Well, because you learn some local, convolutions are local in nature, so the computation is local. So essentially you learn some local functions that learn to look at the local visual context and predict, is this a good peak location or not? All right. So if that context moves a little bit to the left or to the right or in front and so on, that function generalizes. It still looks at local context. That's why that we say that convolutional networks are translation invariant. The whole thing can translate. Well, the resulting heat map, the output heat map will also translate. All right. This is extremely important. If you cannot generalize other basic translation of the objects, then forget about generalization or doing anything useful as a robot gripper. The only thing you will be able to do is when the objects are exactly on the same locations as what you are trained on. Our goal is to generalize beyond the training distribution. Now, this may come as a surprise. Why? Because in many reinforcement learning papers we saw, there was no difference between train and test. There was only one environment. Your goal was to discover, right, the right policy in that environment that would pick up the mug, or we push the object to the desired location and so on. I would not test your policy by swapping objects, by changing the background color and so on, right? You would be evaluated exactly on the environment where your reinforcement learning policy were trained on. Do you kind of agree with this? Okay. Well, so there has been a recent movement, let's say the last 1-2 years, about generalization for reinforcement learning. And people understand now that, RL is a way to come up with actions. Asking the expert is also another way to come up with actions, but requires, human involvement, for example, right? And beyond the discovery, there is also the transfer. We want to discover a behavior and we want to be able to transfer it to related other environments. Does this make sense? Now, imitation learning methods, because they don't need to worry at all about discovery because the actions are there from the expert, okay? They put all their emphasis on transfer. Correct? Do you agree? Now, what is the reality? What's the reality? Well, the reality is that we, as toddlers and infants and babies, infants, toddlers, and as we grow up, we dramatically imitate, but we're extremely good imitators because we have perfect visual understanding. We don't need behavior cloning. We don't need ground truth actions. We can map the actions of our mom to our hand, which is great. And we are also fantastic at transfer. And we are not imitation learning methods. It's not like we train at training time and then we test. No, if we fail, we try again and we try again. So we combine imitation and reinforcement learning, but the reinforcement learning is self-guided reinforcement learning. There's no extrinsic reward. I know I need to open the jar to get the chocolate cookie. If the jar doesn't open, I can perceive it and realize that I'm failing in the task. So there is a dramatic visual grounding problem that I'm solving, like learning visual representations about the tasks, what I'm after, the goal, how the goal looks like, where the different objects and entities and parts I'm looking for are. I track them in space and time. All this happens. And this supports my reinforcement learning, automated reinforcement learning method in the real world. And we're extremely also sample efficient on our exploration. We don't just add noise, right? We're very, very targeted on trying different strategies. For example, you try to open a door. First, you push towards out. You see it doesn't work. Then you drag it in, right? Then it works. If it doesn't work, then you say, okay, it's stuck in different ways. So you are really intelligent how you explore and you try alternatives. But does this make sense? How imitation and reinforcement are put together in general to build intelligent agents? Now, this doesn't exist yet in the literature, but people do realize the importance of both processes. So we do expect to see amazing solutions on that regime in the next months and semesters. Okay, so let me not say years because that's a fact. Does this make sense? So things are happening now and changing. People all the time look into this problem. Okay. Now this method does not worry about reinforcement whatsoever. It has a clear train and test, so it's a very pure imitation learning method. That's great, but it's really worried about generalization and put emphasis on how can I parameterize my actions for pick and place and scene rearrangement so that they can generalize under changes of the scene, let's say. So we're not gonna, once we have a heat map to predict our pick location, we're not gonna go and look at the patch and predict dx dy, how I need to displace it. No, we said that again, we're going to be convolutional. How exactly? Does anybody remember what was the placing prediction, the place prediction? The pick, I assume everybody remembers. We take the image, we put a CNN, spits out a 2D heat map, right? Much like, for example, key point detection. Want to find the key point of a human person is exactly the same. Take an image, put a CNN or some other 2D processing network that spits out a heat map over pixels, correct? So this is precisely the peak prediction. Does anybody remember to tell us, okay, great, I need to pick up the object from there. There's also an intended goal of where I need to place it, okay? That basically is communicated implicitly by training examples in the task. How do I predict that placing? Does anybody remember? Yes?
You involve that local feature map of the pick location with across all of it, and it will match the most with and that'll give like a place score for each of the locations that corresponds to a translation and rotation.
That's correct. So your colleague said you'll go to where you're picking the object, you'll crop the feature map. There's also a rotation component, so you rotate it, I think, 36 times. Okay, so you have 36 rotated patches, and with each one of them you do a cross convolution, and it doesn't need to be that the red and the target match. For example, the red object can be a strawberry and the target can be a yellow plate. Okay, so it doesn't matter, but you train the resulting convolutional map to be picked at the placing location of your expert trajectory. And it's the job of the network to figure out how to correlate the one feature of the strawberry to the yellow plate. Of course, they're dissimilar, but it's going to figure it out and predict, yes, place it here. Okay, does this make sense? Okay. Now, of course, clearly, if I put the strawberry in the yellow plate in a particular location, I may as well have put it in a different placing location. But you do not need to worry about that. So the network may not learn that. But if you give me enough examples where strawberries are placed sometimes on the left of the yellow plate, sometimes on the right, then this multimodality will show up on the placing heat map, okay? And that's the beauty of having a heat map, like a softmax over pixel locations, that multimodality can be handled. While in regression networks, like some people wanted to predict GXTY, this would not have been possible, okay? That's a big part of why we use this. So here is what your colleague said. Let's go grab the features, do some convolutions, and then the result features, we train them so that they pick. So please don't get confused that there is a matching. We don't do some, I mean, it is a matching, but we train so that after convolution, the features pick up the placing location. Does this make sense? So your patch and the placing location don't need to match visually. It can still be similar. It's just that this is a good inductive bias, this crop and convolve. Any questions here? Okay. It's just a convolution. Right. So it's called transporter networks exactly because we are transporting the object. We slide it over the features of the image, and high in the product means that we have high correlations and they're more likely to match the features and so on. And yeah. So that's it. The important thing is this equivariance, that as the image translates, then the resulting heat map translates. Now, there is something I have to tell you. You can train this for very few demonstrations. Now you go and you change the background from black table, make it green. Things will fail. Okay, so things will fail. So it's not that this is a super, let's say, generalization method. There are no objects, explicit objects. Of course, people have built on top. We may see some approaches of that at the very last lecture to put some, let's say, knowledge of objects in that framework. But still, in comparison to these regressions that people were doing before, this is doing much better. That's all we're trying to say. That's why it has been adopted, I would say. Okay? Let's see. So we rotate the patches, and crops can be any size and so on. Now, test time, what do? You just look at the heat map, you take the argmax, and you go with your robot, you pick the object, and you estimate the rotation, because out of those 36 patches, the one that fires, you have 36 heat maps, the one that gives you the argmax, you read off the rotation of your gripper from that one. Does this make sense? Okay. Yeah, so that's precisely also why we have multiple place heat maps, one for each rotation, okay? That's why you say a stack of heat maps. Any questions here? Any questions on the architecture of transporter networks? Okay, so then if you don't have questions, I want to ask you, the expert trajectories give us pick and place locations, all right? So these are the positives. Which are the negatives? Because when you have a heat map, you also need to have negatives when you train it. So what are the negatives? So the positives is exactly where you picked and exactly where you placed it. What are the negative locations? Yes?
Everything else?
Yes, everything else. Much like human pose estimation, the human says this is the human elbow. Everything else that is not annotated is not a human elbow. Now, if you want, some people put a gray area. They say, okay, here's the ground truth. Let me put a ball, right? There's some Gaussian here. Make sure I don't place any loss around nearby the ground truth pose. And then all the rest I put, I consider them negative samples. So that's also you can do. All right. Is that clear? Okay, great. Okay, so now here is another very important design choice of transporter networks. They have their tabletop environment, and the camera may be looking at it from different viewpoints. They only operate on overhead, okay? Which means what? They take this camera view, and they have also depth, and they use the depth and the image to reproject the image overhead. Of course, you can just put your camera overhead, but if you also have a side camera, you may as well just do the transformation. This is not anything, there's nothing learning based there, it's just a geometric transformation that you do. And then you feed this overhead image to the network, then it's much more natural to predict pick and place locations in an overhead map, okay? So let's see how things are going to look like. There's a video here. Right. So that this convolution with the patch, the picked patch, can be thought as an attention between the key, which is what you detected, and the query of all the image. And here is the robot can infer the pick and place maps and went and does it. And this, by the way, works both for two-finger gripper, where you need to be predicting, where should be the center of this gripper, okay? And you go with an open hand, you put in the center in a fixed location from the floor, and you just close your gripper. And it's even more handy for a sanction gripper. Does anybody want to tell us what are the plus and minuses between a two-finger gripper and a sanction gripper? A sanction gripper is like a vacuum, right? It just sucks the object with only one contact point, okay? Who attended Sid's talk where he had a fantastic video with all the failures of a sanction gripper in Amazon? You attended? Or?
No, I didn't.
No, you didn't. Okay.
What you mentioned about it last class.
Okay. So what did I say?
If you use a suction gripper on a book, for example, then when you pull it up, the under pages will sort of flop down. That's true. Yes, exactly. Or if you have a box and the box opens from the top, again, you're going to open the box and you're going to mess it up. So there are problems with the sanction gripper if you don't have a pay attention of, or even if you pay attention where you're going to pick. And sometimes, this type of two-finger grippers can help you in those situations. Okay. Yeah, but definitely sanction grippers are dramatically used in industry and so on. So now these networks can be trained with as little as 10 demonstrations. Models that I'm going to show in the last lecture can be trained also with a single demonstration. This doesn't say much though, because it all depends how much you vary the train and test time, right? So this is something that actually is not, very well described, let's say. So here the task is to take any block and to align it to that corner. So here this one picked it up twice. Okay, did you see? So one task may not involve only one pick and place. You may have multiple pick and place. Okay, so the expert may have done multiple pick and place for you to succeed in the task. All right, and since we have multiple pick and place, at some point, this robot needs to decide, should I do an extra pick and place or should I stop? Okay, so how do you think this is handled here? That's pretty important, by the way. We humans totally understand when we got it, and then we know when to stop. Okay, so, yes?
You have some threshold on the score of the pick and place location.
So you're saying that nothing is going to... Well, that's one thing, and precisely because this does not work well, this is a big, let's say, weak point of this method. There is not a good way to understand when you're done, okay? Now, this you may think it's a small thing, but actually is a big problem of our robots being trained for just predicting actions as opposed to all the other information, meta information around the task. What does it mean to succeed? Do you have an explicit representation of your goal or not? And so on. If you had an explicit representation of your goal, which you can imagine that it's just a visual detection problem, right? The same way you detect the book, you may be detecting, oh, did I put this box into the right corner? It's just a more complicated concept. Mode relation is not unary. You need to take into account the structure of multiple components to figure out if you did it, okay? And although we are very, very good now at template matching, finding books, finding cigarettes, finding tiny, bottles and so on in the kitchen, etc. When a concept has multiple components, all right, for example, did I make a circle? Did I put the object inside the ball? Is indeed my tower high enough? Is the door opened, etc.? So more fine-grained concepts, I would say the detectors still struggle, kind of, okay? I mean, you can train them for sure, but they struggle, and this type of goal detection has not been incorporated here, although it is an obvious thing. I mean, if you wanted to extend this framework, sure, you can take pictures of the goal location and train, featureize them and train contrastively to say yes when the goal has been succeeded and no otherwise. So we'll discuss in this course about the clip model, okay? Just takes a language and an image and predicts whether a language goal holds in the image. Something like that also you could have done to extend this framework. This is very reasonable. Does this make sense?
the task of goal detection. Did I succeed or not? To have a more informed done signal, as opposed to looking at the action and say, oh, my peak heat map doesn't fire, I should map. Instead, even if I'm a robot, I don't have any gripper, I should be able to have these concepts in memory and say, is this indeed the red cube in the yellow ball or not? Does this make sense? So we don't need the grippers. The concept detection problem is always there, even if you have, let's say, some intelligent Alexa. By intelligent, I mean, Alexa is already kind of intelligent, but with a camera that is able to look at you in the kitchen and say, yeah, you burned the egg. No, you didn't burn it. Oh, now you know. So this is all, the problem is still there. Does this make sense? Action prediction is just an extra problem. So the common sense of the activity, no matter what, we need to solve it, whether we have end effectors on our robots or not. Does this make sense? Okay, actually now this reminds me of, so Oliver Cromer, who is an RI, professor in RI, had said the following. A big part of cooking process, because a lot of companies care a lot to develop robots for cooking. Okay, so now this is a nightmare because me, for example, I have difficulty peeling the potato, let alone the robot. But what Oliver said is that a big part of the cooking process is just waiting to see when the thing is ready. You go on top of the casserole, you're like, okay, now we're ready for the next step. Oh, now we're ready for oh yes, I think it burnt, and so on. So this goal detection problem is there in AI no matter what. No matter where you have end effectors or not. Because you may not have end effectors, but you may have a voice and say, you need to come. I don't know, the food is ready or something. Does this make sense? Okay, so this was simulated results. So these are some real world. All right, so what is this task? This task is of stacking one ball into the other. The expert picks up the ball with the sanction from one location and puts it in the other. By the way, just to be clear here, as you see here, we're using a sanction. Do you recognize that? Okay, so how the expert demonstrations were given? Who gave those 10 expert demonstrations or 50 or 100? You control the robot with a sanction gripper, right? Yeah. Exactly. So this is very important. So this is kinesthetic teaching. You take the robot's hand and you do the job and you have the action ready. You have the pick location and the place. Does this make sense? It cannot be, no, you put your hands and you do the motion. We'll discuss. We have a whole lecture on visual limitation where you can be using your hands if you like. All right. So, but this will come later because kinesthetic teaching is more advanced comparison to visual, to learning from observations. Yes?
If you got something from the suction gripper, can you rotate it?
Yes, you can.
They don't seem to do that at all in the example.
Exactly. So in this example, maybe rotation was not important. For example, if you tell me put the blue cube in the yellow ball, I don't need to rotate the ball, correct? Or if you tell me put that blue thing in the blue plate on the yellow plate, I still don't need to rotate. However, I'm not sure if you saw a task in the previous, it hasn't come yet. You'll see some other tasks where, for example, if you'll see what I mean. The toddlers have some very nice letter-shaped holes where you really need to pick a letter and put it inside and so on. Oh, here it is. So this task where there are holes and shapes, it does require rotation to be able to enter in the right hole, okay? Okay, so here are some tasks that they considered. Now, the important thing is the following. If I have multiple tasks, correct? How do I train transporter networks? If I have multiple tasks, every task will come with a set of training demonstrations of pick and place locations and rotations, right? So can I train across multiple tasks the same network? Yes?
Maybe if you had another input for the goal.
Excellent. Yeah, precisely. Exactly. Because if you don't, I can totally imagine, for example, let me show you a previous example here. Not data augmentation, where there was this here. So the goal is place red in green. If you don't, this doesn't enter the policy, if I show you another task where you place the green in red, then you're going to mess up the pick and place locations. So you really need to feed as input a description of the goal. Is that clear what your colleague said? Okay, great. And what description of the goal do we feed? That's a very good question. By the way, this is an open research problem. What is the best way to encode the goal? One local optimum that people have found on recent papers is to just feed also the language command. The language command. For example, here you take place red in green, you feature it with the, some language encoder transformer, and you feed it into your policy. And this is precisely what we're going to see in the last lecture. Do you see any negatives on communicating the goal as language? Yeah?
It adds a whole other task that you have to learn, and there's some ambiguity to say place red and green. You can say place the red balls in the green.
But you can say place the red cubes into the green ball. I mean, I can make a little bit more comprehensive instruction. Okay.
It's adding another task to it, the language understanding.
Yes. Okay, sure. But you know what? For language understanding, you are not going to use some external training data. You're still going to train only from demonstrations. But actually, this is a very good question. So now your colleague is saying it adds the extra task of understanding language. And what does understanding language means? Well, one person can say that understanding place red in green means that if I show you a scene where there is a green and the red, you'll be able to do the right thing. That's it. Some people will say, as long as you have a goal condition policy that take the language and spit out the right actions, this means that you understand language. Another person may say, no, this is not language understanding. I should be able to understand language without seeing anything. For example, I can say an elephant jumping on the keyboard. I can totally see, okay, is this elephant? Oh, the poor keyboard broke, etc. Do you see? Without any language, without any using my end effectors, I just understand language because I know the concepts you're talking about. I simulate them and I predict the result. Does this make sense? Now, but this is a great thing that your colleague mentioned. And you will see that at the last lecture, we'll do exactly what you said. We'll take a language, featureize it, feed it into our policy with some very interesting wiring of which features touch what are visual features and so on. And that language encoding will have been pre-trained from tons of passive images of green cubes and red balls. And so that language pathway will have understood things about objects and their arrangements and so on. All right. So we'll share the weights with this other network that was trained to do exactly this caption detection task. Let's say that we're going to see. Okay. But great. This is great. Do you have any other questions? Okay. So here is the swiping task. So the swiping, you use a spatula, okay? You can hold the spatula, no problem, as long as your demonstrations is also given with the same spatula, all right? So you can use a spatula to, put the pose 1 where you place the spatula. Pose 2 is where you drag the spatula and then you take it up and again you place it somewhere and you put it again and so on. And this swiping piles is an example of multiple actions, okay? The network doesn't have an idea of time. You just look at the scene, predicts a pick and a place. Now, we call them pick and place abusing the notation. This is just, start and end pose of the gripper. That's it. But does this make sense? So the policy does not integrate over time or being some recurrence over time on some temporal attention, nothing. It's just instantaneous. You open your eyes, you look at the scene, you predict swipe the pile, all right? Now, do you see any problem with this? What could a policy that has some understanding of time do? Yeah?
Account for maybe the momentum of the objects if they push it.
Yeah, exactly. So 1 second, but this method does not take into account the momentum. It's quasi-static. You just put the gripper, swipe it up, right, and so on. However, one thing that I would like, let's say, to be able to infer if I'm a robot, imagine that those red piles were stuck on the table, like we're like sculptures. You cannot move them, all right? So you try to do the pick and place, you see nothing changed. You need to realize, okay, I think there's something wrong here. So you can do what is called progress monitoring. So here there's no progress monitoring. You will be doing swipe of these sculpture piles forever, okay? Because your peak softmax will be high, your place, and so on. So you'll be just doing the same thing, and you won't be able to realize that you are not making progress, okay? All right, but here you can do all crazy things like manipulating ropes and so on, and you can train a network for every task. And here you can also augment this transporter network, as you can see, with some 6 degrees of freedom. So far, we were using only, 2, like this type of rotation and where to place. By just predicting those extra parameters as a regression on the particular location of the workspace. And here is a real experiment. And as you see here, when you place the little bottles, you really need to worry about orienting them in the right way on the bag. Same way with the pieces, okay? And the go positions. Any questions here? Well, I think this is actually progress over industrial robots that don't have any camera. They may not be able to generalize to, placing positions of the bottles that is blue as opposed to white. Then things are going to fail. But you know what? If you're in an industry, maybe you have a lot of those type of placing little bottles to this identical placement locations, and you should be able to handle small displacements and so on. So I think this is pretty useful as a prototype system that has vision and can do accurate pick and place. All right. Okay, so they show here some results. And the most important thing is their baselines. So they vary the number of demonstrations, that the training demonstrations, 1, 10, 100, and 1,000. And they compare transporter networks with that have very, very good performance with methods that actually you go through this MLP bottleneck. Okay, they take the image and they condense it into 1D vector. Okay, and you see here how dramatically that MLP prediction that we had discussed last time actually fails to execute the task. Okay. All right. So what you see here is the fact that the placing heat map can handle multimodality. It doesn't need to have a unique peak. If there is essentially a multiple set of solutions that are valid, they are all going to light up, as you can see. All right. So we know that this is not possible with regression networks. Is this clear? This is a very important point. Okay. So now this slide is very important. And small analysis on the ability of transporter networks to interpolate and extrapolate. So here is the red block, and imagine that I trained it to place it on those 3 locations, okay? So I give it 10 demonstrations where the block starts from there and can be placed from any of those locations, let's say. Okay, now, so the convolution and MLP, what is convolution MLP? You take the image and you do convolutions, and then you flatten the features, and then you pass them through an MLP, and then you predict where on the image to pick and place. As you see, it cannot do well far away from the training data. You see that the blue dots are precisely on the gray points that were given at training time. All right. Why? Because once the image is translated, this flattened feature vector changes dramatically, and the MLP has not learned how to generalize to those different flattened vectors. All right. Now, here is another MLP. This is called GT state MLP that uses directly the location of the object. And as you see, it can do much better. It has much more blue. Do you agree in comparison to the image? And it takes the ground truth state and map it. So that state, of course, is much shorter than, you know, flattening image features, and maps it to the ground truth peak and place. But far away, as you see the circle, again, it fails. All right. It doesn't know what to do when the object coordinate, instead of being, let's say, 0, 0, is a -5, etc. Now, here is a transporter network. It's blue everywhere. All right. So it really generalizes from 10 demonstrations thanks to its equivariance. Does this make sense? So you kill these equivariance once you put MLPs. Equivariance is all about sparsity of computation. The output values need to depend sparsely on the input, not on everything, because if that everything changes, then your output was going to change, right? So if you know how to pick up this pen, if what's next to the pen changes, it should not affect your peak location, right? So with convolutions, this can be achieved. Now with transformer networks that have these attentions, this is even more robust because you can attend, and these attentions can really discard the irrelevant context if you give them enough augmentations and training data, okay? Augmentations, I would say. So is this clear? This is a very important slide. Okay. So next, we're going to go to goal condition transporter networks. This is related to what your colleague discussed earlier. How do we actually give them a particular goal? And we discussed about language goals. In this work, we're not going to be giving language goals. We're going to give image goals. So this is a little bit not the easiest way to condition as your goal, because you ask the robot to achieve the task and you need to feed it an image, a goal image. Does this make sense? That you will only have at your disposal if at some point you achieve the task, so you know how it needs to look like, and now you rearrange the scene and you tell the robot, look, this is still your goal. So it's a very trivial extension of the framework. As you're going to see, we're just going to concatenate channel-wise goal and input image, and that's pretty much it. And you will see that we will be able to achieve the goal. Now, you didn't really reply to my question earlier about what is the problem of language goals. I mean, you made a very awesome comment, but I want to mention the following thing. Imagine that with your parents, and your parent teach you on Monday, okay, here's how you need to make the table. And then, it's a multi-plate process, so you need to put the plate and the smaller inside, and then a bunch of forks here and spoons there, and then knives there, and then the napkin, and so on. Okay, so there's a lot of stuff there that you were able to pick in place. And then next day they tell you, make the table. So your goal is going to be make the table. Okay, so now the poor transporter that will just take this language, okay, cannot easily recover all this information. Is that clear? So all this needs to be memorized on the weights. So I can tell you that you will fail 100% because the steps are not explicitly memorized somewhere. Okay, so that's a problem of language, of communicating goals through language and using that language to directly predict pick and place locations. Potentially, you can use the language, but this language better be used to retrieve more descriptive representations of goals as opposed to the language directly. Do you see? So the language should be grounded in your memory of what you did on Monday to repeat on Tuesday. Does this make sense? And I do believe that in the future months, there's going to be many papers that will use explicit memory of things that the agent achieved and retrieve to repeat. In fact, we will see an amazing paper, Go Explore, that shows this external memory to do intelligent exploration, but this is going to be in our intelligent exploration lecture. Does this make sense? Okay, so here is a very simple task, a very simple framework for goal conditioning, simply because I want you to know about it. So this paper has a first author, Daniel Seita, who is a postdoc with David Held in Robotics Institute right now, so you can go and talk to him if you like. And along with goal condition transporters, which means extending the transporter framework to be goal conditioned, they also contributed a simulated benchmark of manipulating deformable objects. Now, as you just saw, this is a bug. Now it's interesting that when you see a static image, it doesn't look like a bug, but as soon as the robot picks it up, we all understand it's a bug, which shows the importance of motion for perception. But in any case, these are bugs. Okay. So here it is. So they're very excited about deformable objects, deformable object manipulation, and so on. So basically, they propose a suite of 12 simulated tasks in PyBullet. So preparing this simulation environment, it's a huge pain. So they give it ready to us. This has to do with ropes, and it has to do with necklaces and bags, etc. And here is the extension of the architecture. It's extremely simple. The only thing we're going to have is an extra goal image. Okay. So what you see here as goal OG. Does make sense? Is a goal RGB image that you don't need to worry where it comes from. It is given by the benchmark. The goal of the agent is to use that image and the current image of the scene to achieve the task, which means to move this guy here. That's what I infer by comparing the input image and the goal. Okay, so how are we going to do that? Well, there is here a network that takes as input the current image and spits out again the peak features, same as before. All right. And so the current image is featurized in multiple ways. One is these features, and the other is F query here and F key. Okay. And here's the goal image that is also featurized and is also passed here on the peak, because the where to pick needs to be able to look at that goal image. All right. Again, here is the argmax, same as before. So the peak location will be the argmax of the resulting features. Okay. And now what we're going to do is we're going to pointwise multiply goal features with the input query features. That's it. So the input image and the goal image are going to interact by channel-wise multiplication of their feature maps. And again, we're going to crop here. From this complicated image that takes into account both the goal and the query, we're going to crop our patch, which we're going to rotate again 36 times, and we're going to convolve it to the placing, so the same featurization of the input to predict the place location. One second. So we crop this guy, and this is the resulting, this is the heat map. So this is the goal and key. So the input image is featurized twice, one to provide the query features and one the key features. The query features are combined with the goal to generate where you need to pick, and the key features are combined with the goal to predict where you need to place. So we crop from the pick, we convolve with the place, and we predict the heat map. So this is precisely where you need to place, and this is precisely what you need to pick. Does this make sense? Now, this feature-wise, channel-wise concatenation has tremendous limitations. If the object between the input and the output has been moved quite a bit, the convolutions will not be able to see that move, okay? There are other methods for example, for David Heltz, again, for deformable objects, which what they do is they assume again a goal image and an input image, and the only thing they do is they compute an optical flow between input and goal. So optical flow is where every pixel transports between the one image and the other. And precisely these displacements that you infer through optical flow computation are exactly where you need to pick and exactly what you need to place. Okay, so it tells you how exactly you need to transport. And optical flow, we know that is equivariant. Does this make sense? Okay, so that's it. So they have tasks with cables, they have tasks with bags and so on. Now, the good thing is that you can train one policy across multiple tasks. Okay. So the demonstration data, each time as you see, you give exactly identical image for each pick and place. If let's say your task has multiple pick and place locations, you always use the same final goal scene as you see that, let's say C, the final C that the cable needs to form. And that's how you train your, that's how you train your goal condition transporter. Is this clear? Mm-hmm. So basically, the only thing we did is we took the input image and we generated two different feature maps we concatenated the goal. From the first feature map, we cropped the patch, we predicted where to pick, we cropped the patch, and we convolve with the other to predict where to place. Do you see how simple it is? All right. So here is again demonstration data of how would you move about to move that little piece of cloth. And as you see, the goal is always the same. Do you see the goal being the second image? This guy is always the same at every time step. Okay, so you don't fit the immediate sub goal, you fit always the final goal. Is that clear? Okay. Okay, great. So here is again the architecture. I think it's copy paste of the previous thing. So here is the current image that enter on three networks for the pick, the query, and the key. Here is the goal image that is featurized from the F goal and enters into the pick because we need to condition the pick on the goal. Okay. Great. So we take the goal and the query logics to generate the placing heat map. And again, the goal and the key logics for the to do the cross convolution. We crop the patch from the first and we convolve in the second and we predict the output heat map. Is that more clear now with the wiring of the information? Okay. This means point-wise multiplication of the feature maps. Does this make sense? So they only interact channel-wise. Okay, so every location is only multiplied with the corresponding with the feature of the corresponding location from the other image. Is that clear? Okay. So the highest score is the placing point. Sure. Well, this is pretty much what I wanted to show you. And here is the result on the simulated with a simulated benchmark. So here we have multiple steps, as you see. We open the bag, we put inside the object, and then we pick up the bag and put on the green. And these multiple steps has been just shown by the expert in different, exactly like we showed in the slides earlier. Does this make sense? Yes.
Does the goal, this is still where the goal is being input as an image?
Yes.
How does it know that the thing has to be inside the bag? Because it's not going to be visible very clearly in the goal.
Yes, it's not going to be visible very clearly, but that's exactly how you train. That training time, again, the goal was a yellow bag, right? And the pick location was the red cube, right?
Okay. Oh,
Yeah.
we change for steps.
Yes, every step has the corresponding action. It's not that you say, okay, here's the final goal, figure out what to do in between.
But the goal is like the bag is now in the green square with the block inside it.
No, 1 second. That's precisely what the goal is. So this is what I actually showed earlier, and that's pretty important. So it's actually extremely straightforward to train. Okay, here is it. So the demonstration data are, maybe I should find one with goal bags. Okay, this is not the bag, but so here, do you see the final goal? The final goal is multiple steps away from the current image and is always the same in all 5 steps. 1, 2, 3, 4, 5. They all have identical goals. So the same for your example with the yellow bag and the red cube, the goal is always the yellow bag without the cube. Okay, yeah. But you know, I mean, sure, the red thing is not shown, but as long as you train it to put it there, the network is going to remember this in its parameters. Does this make sense? Now, if you have 2 things, if you train 2 tasks, in one you throw away the red block, and the other you put in the bag, the network is not going to be able to figure out which one, except if the goal really shows one bag to be much more full than the other. Okay, is this what you wanted to say? Yeah, great. Other questions? Yes?
How does this know when it's done? It seems like the image could either be very specific or the goal could be very general, but the image is always the same. Like if I want to put 2 blocks in a bag, the image would have them rotated a specific way, but me as the end user might not care about the rotation of the blocks.
Yes. Okay. So actually, can you repeat your question?
I guess, how does it know in general when it's done?
In the same way, the non-goal condition knows when it's done. Doesn't have an explicit matching between the goal and the image. It just concatenates and spits out actions. And in fact, they've done for some experiments, this is a good question. In the experimental section, they say we stop the robot after a predefined number of steps, something like this, okay? Which is not very satisfactory. Now, another thing you can do, what I would do, for example, is I would take the goal, the goal image and the input image, and I would do some fusion with transformers, and then I will spit out matching, non-matching. So I would train that module. I would call it goal detection module. I would call it. I would pre-train it like hell to some passive observation data and fine-tune it on this task, and then I would trust it to tell me, yes, you succeed on your goal or no. Yes.
So if, let's say you like, in a real company, you would maybe switch out the product because it's not cost efficient. And so you change it out for something that has different material properties. So the bag, it doesn't deform in the same way it used to. Would you have to retrain the network, or would it be adaptive? Yeah, no, here we don't have any adaptation of any sort. To be able to adapt, you need to be trained with a lot of different bugs. Okay, so if your training data contains multiple different bugs, correct, and then at this time one of those shows up, I will be able to, adapt. If you show me a new bug that I haven't handled, or it opens in a very different way and so on, I mean, naturally, I may not be able to generalize, okay, right? And also because I just copy paste, I don't try to say, oh, it seems that I got stuck in this step of the process. Let me try again. So I also don't have any clue about how far in the process I am. I mean, I'm not saying that you cannot augment the framework to do that, but it is not there right now. Okay, there's no progress monitoring. The only thing that is there is image to action mapping, image and goal to action mapping. That's all is there, right? And we know to make an intelligent, let's say, exploration and reasoning and common sense, you may need to have 2-3 more extra modules. For example, progress monitoring, and part of progress monitor is in which part of the process I am, so which sub goal have I hit, and did I also hit my final goal? Okay, yes.
I was still a bit confused as to like if your final goal is the yellow bag square, how do you make sure your agent performs the action of putting the blocks in the bag versus like the action of throwing away the blocks out of the space?
Great. So because you never trained your agent to throw away the block, that's the thing. You never trained it like that. So this action is not available for the agent. It doesn't know about that. Okay, it only clones what you showed it to do. Okay. I mean, you can show the demonstration to throw away the block. You can fit the demonstration like pick and place outside of the table, sure. Where its hand still reaches, right? Because you need to reach. Okay. Does this make sense? And then it's gonna arbitrate.
Certain objects you want to be placed in the bag, and certain objects you want to be thrown out, right?
But you can teach it like that. You can train it like that. So in that sense, it's flexible.
Okay.
Do you see?
Yeah.
Yeah, you can totally have 5 objects here on the scene. Put your goal there with a bag. Now, if at different times you want different objects inside and different objects outside, now, for example, in this task, I want these 2 inside and these 2 outside. Well, this needs to communicate it with the goal, as your colleague said. So if the final goal cannot visually discern between the goal images of these 2 tasks, your agent won't be able to get it. Now, you can add an extra language if you want. That's okay. But if this is what you mean, yes, in that sense, you may not succeed. Yes.
Since the goal is based on an image, does that mean that when you're testing it, you have to test from the demonstration set?
Exactly, yeah. At test time also you assume an image. Yeah, somehow you need to have an image of the task, right? Yeah, which is a little bit weird, but that's how it works. An image of the goal task, I mean. Okay. Well, I think we're kind of done here with the goal condition transporters. Yeah, we saw that. Okay, great. So now we're going to switch to our model-based introduction to model-based reinforcement learning. Do you have any questions here before I start? Okay, so this is the first lecture of a very big chapter in the course about model-based reinforcement learning. So far, all the reinforcement learning methods that we saw and the imitation learning methods did not try to learn anything about the transitions of the environment, okay? Well, when we did the dynamic programming lecture, long time ago, we had knowledge of those transitions, okay? Now, unfortunately, it was a little bit hopeless knowledge because it was a tabular method and the number of states was enormous. So there were nothing useful that we could do with the model that we had in our hands, unfortunately. Now, today's lecture, we're going to do an introduction of what is model-based reinforcement learning, and we're going to see a method that learns a model in a very simple setup. And that simple setup is the setup we have a very low dimensional state of the environment, which means, you know, here is my object or my gripper, here is the 3D locations of them, and I have, let's say, 10, 15 numbers that describe that state, and I have access to the state, and I just want to learn transitions of that low dimensional state. Now, on Wednesday, we have some insane, exciting lecture where we're going to assume we know the model of a very complicated environment like AlphaGo, and we'll try to essentially plan to really learn intelligent policies in that environment. That's one thing we're going to do. We're going to try to do this with and without demonstration data, okay? Completely reinforcement learning trained, as well as with human supervised actions. And then we're going to throw away that complicated model and we're going to learn it and see if we can repeat the process and still learn amazing policies in the game of Go. Now, in next week, we're going to see, great, so we solved Go. How can we go about the general world? Can we learn general models that generalize and help us train policies and so on? Okay. So here is our reinforcement learning diagram. We've seen this many times. And the model is precisely this part, the Earth, is accepts actions of the agent and responds back with changes of its state, okay? And these dynamics that was inside the probability of the trajectory star, if you remember, they would always cancel out. This is precisely what we're talking about. What's the next state given the present state and action, and what's the reward? That's all. So this is the model. So the model is a transition function plus the reward. Input is state and action, output is reward and the next state. That's all. So the idea is that we're going to have a parametric function that we're going to train to represent that state transition. So we're going to learn this model in the beginning, at least with maximum likelihood. We're going to maximize likelihood of transitions. How models can be used? This is very important. These 3 bullets are very important. Three things. So the first is that when you have a model, you can unroll it forward. You can unroll it, which means what? You can predict the next state. The next state can feed again back in the model to give you the next state, next state, and so on, till a state far away in time, which you can compare with your goal, what you're trying to achieve. And then this look ahead will help you select your actions. Do you remember where we did that before? Yeah. MCTS was using a model of the environment, right? You remember that we were essentially sampling trajectories from that known model, and those trajectories, we were using them. We were comparing them with the goal. Back then, there was no goal. It was just a final reward, win or not win. And then we would using this look ahead to select actions in the root node. Okay. And the model was known and there was no problem. So we will see that again with learned models and so on. Now, another thing you can do, which is nobody would think that works, but actually people use it all the time and actually it performs decently well, is that you can take Any reinforcement learning method, it may be as well model-free, soft actor critic, DTPG, TRPO, you'll see a lot of different variants. And instead of training in the real experience, you train it on simulated experience. Unbelievable, right? So you can sample tons of experience from your model. Yeah, and by the way, this if you sample insane amount of experience from model, this doesn't count towards your sample complexity. These are cheap samples. I mean, of course, the GPU need to generate them, but you don't need to act in the world, right? So you are really not penalized. When the sample complexity, when we talk about the sample complexity of a method, how many samples it uses, we mean actual world interactions. We don't mean querying your model. You can query your model as much as you like, okay? All right, and the third part, which we're not going to see anytime soon, but it's going to be later, on our, learning with self-supervised representations and so on, we will use that prediction of the future to learn visual representations. And to be honest, this is pretty central for AI. Let's say the brain learns by predicting the future. That's precisely what they mean. We learn visual representations simply by predicting the transitions of the world. Okay, you form a transition, you think, oh, I think this is going to happen. You see what actually happens, you compute the error, you backpropagate to your parameters. Next time you predict better. All right. So basically, we're going to use next time prediction for representation learning, and this is terribly important because the better your representations, the better the policy you're going to learn. But you don't need to worry about this right now because this is going to happen in later lectures. So let's look a little bit about the red, real quick, because we've seen it in MCTS, as correctly you guys pointed out. So unrolling essentially means that you have an action sequence, you feed it in your model, and you get a corresponding, prediction of rewards and states. And these predictions, we denote them with hat because they're not ground truth. It's what the model thinks, okay? And then your goal is either to reach a goal state S star, or to maximize your rewards, sum of RTs, correct? And basically, the Monte Carlo research we saw was a special case of the latter, where there was only reward at the final state, if you remember. I mean, to be honest, with Atari games, this didn't happen. There was no reward at the final. In fact, if you remember, we even cut the trajectories that we enrolled, and we would collect the sum of rewards along that trajectory. Do you remember? With the divers that our trajectory were not long enough to save 6 divers. So they were intermediate rewards then. So this falls totally under that second case. All right. So this is what it means. Now the question is, how do we solve that crazy optimization problem, which is I want to find the action so that I maximize the reward or I reach the goal state. And Monte Carlo research was one way to search, right? Very reasonable way of searching over that, trying to optimize that problem. Does this make sense? We had a designated root node. Our goal was to find the first action, if you remember, and we were, sampling and building this tree to collect more information of the queues of the different intermediate actions, improve our in policy, and so on, trying to solve that optimization problem, essentially. Now, today, you will see a terribly simple way to solve the problem, which is with a cross-entropy method. So basically, you can just use evolutionary search, which means what? You have an idea, you sample a bunch of action sequences, let's say sequence of actions of how many is the length of your action sequence, let's say 10 actions. You feed them, you see which one gave you the highest reward, okay? And then you sample more around these elite, let's say, action sequences. Like very, very straightforward gradient-free optimization, okay? So the paper we're gonna visit, and you will need to actually implement in your homework, we'll use this very simple cross-entropy method, okay? Is that clear? All right. Now, one way to handle model errors, unfortunately, the longer you enroll in the future, the higher the model error, is to use model predictive control. So what does model predictive control means? Is actually very, very simple. It means that you do the search over a sequence of actions, okay? But you execute only the first action. And once you execute the first action, you actually apply it in the environment, you see the ground truth next state, and then you search again, okay? You don't, while the previous search problem, if you remember, was an optimization over multiple actions, you see A1 till A capital T, yes, you search over all of them because you need to figure out where you go, but you only apply the first one. And if you remember, in Monte Carlo research, we did exactly the same thing. We're searching over everything, but we only applied the first action, in the environment, like with the opponent who was waiting for us to play the move. And then we will see the actual next state, and then we'll play again, despite the fact that there the model, by the way, was ground truth. So there is no, let's say, reason to minimize model error, but you maximize your search capabilities if you actually know what happened and how the opponent played, as opposed to staying there and try to hypothesize what the environment wouldn't send you. Okay, is that clear? Obvious. This is obvious. Model predictive model is a very, very obvious idea. So we replan at every time step. Can somebody come up with a negative of replanning at each time step? I mean, it helps error accumulation through unrolling, but what is the downside? Yes? Yeah, in the sense that you're searching again, yes. Although you can totally keep around your elites as your subsequences, right? But I think you said it correctly. We do need more compute. Of course, if you search once versus if you search capital T times, naturally you need more computation. Okay. Benefits of model-based reinforcement learning. Who would like to say something here? I mean, I know some people have come to me in the office hours and they're excited about model-based RL, so I'm just wondering if you're too excited, you can just say something about it. Mm-hmm.
I mean, we talked about 3 things, but when we opened this section, one was planning that we were just talking about now, but another one was the synthetic experience.
Yes, so both of them essentially help on learning with fewer samples in the real world, right? That's the thing. And the other, I'm not sure if this was clear in the homework, but in reinforcement learning, you have a particular reward function. Till you get any non-negative reward, all this experience is wasted. You don't learn anything unless you are rewarded. So this is extremely wasteful learning, right? That's why we say that the reinforcement learning is the cherry of the cake in the AI cake, right? The cherry of the AI cake. Now, on the contrary, if you have a model of the world, you can support learning of multiple different tasks. And now I'm going to show you what I mean by this. So here is a little spider, and you've learned how that spider moves, the next state function. This state, if you do this, here's the next state. And you can give it any trajectory you like as a task, and that spider is going to follow it, okay? Because you can enroll the model, search for the actions that actually indeed will follow with the trajectory. If you were doing reinforcement learning, then you had to train a different policy for each trajectory. This is clearly not the right way to design the task. Is that clear? So here I have another trajectory. I'm not sure if you're able to see those blue dots. And here's another trajectory that makes a half circle. So basically, you can support multitask learning with multiple objectives, learn multiple policies simply by enrolling the model. Now, if you want, if it's a policy that you repeat 100,000 of times, right, then you can totally distill it. You can use your model to find the actions, and you can distill it into a policy network that only performs that particular task. That's fine. For example, you're a barista. You want to really be very quick on how you empty the coffee and then clean it and then feed it back into the machine. In fact, this is precisely what psychology researchers tell us, that we transition as humans from model-based to reactive through expertise. So when you are a novice in a task, playing piano, you are very model-based, you think through and so on. You put goals that are very nearby in the future, right? And then you try to hit them and so on. As you become expert, you are more and more reactive. Same with the dancing, okay? In the beginning, you don't know the dance. You try, it doesn't come out naturally. You have every sub-goal, but as you practice more and more, then you become reactive, and your sub-goals come further in the future, and then you have policies that the goal is really, really far away, and you predict and all the actions come out ready. Does this make sense? Okay. Any questions here? Okay, so learning models, this is the most important thing. Although with known models also, we're going to have a lecture. So when we learn a model, we need to alternate between learning the model and learning the policy. This is not obvious. Somebody could say, I can just, act randomly, collect a bunch of data, learn my transition function and reward function, and then use it to improve my policy. How you're going to use it to improve your policy? 2 ways we just said. So this is very important to remember. number one, sampling synthetic experience from your model. Number two, do unrolling over your model and optimize over your actions. These are two different ways, all right? Now, unfortunately, this does not work. What works instead? Well, the following thing. You have a current policy, and that policy starts from random, and you collect experience. You use this experience to train a dynamics model, okay? Now, you use that model to update your policy by either a model free RL method on a simulating synthetic experience sample from your model, or imitating a model-based controller, okay? So the model-based controller is, so unfortunately I repeated because I didn't see the model free RL. So a model-based controller is essentially the action selection through unrolling. That's what this means. So I'll fix that. This is actually a typo, and then you go back. Now, can somebody tell me why this alternation is important? Why we cannot just act, collect our experience, learn a model, sample from the model, and fit a model free RL policy and be done? Yes.
Because we want to collect relevant information on the environment to where the policy is actually going to behave, or how it's going to behave.
Right.
Rather than just collecting random information from the environment, being able to model that really well, we should model where it's more likely that the agent will be. My intuition. I
see. Yes. To be honest, that's precisely correct intuition. If you act randomly and your goal is to pick up your cell phone, right? In the beginning, you're not going to be able to pick it up. So the model you're going to learn will have nothing to do with picking up the cell phone, and optimizing through that initial model may get you close to the cell phone, but will not lead you to pick it up because just the model doesn't know anything about it. Now, so that's why then you'll deploy this better policy where that better policy will start poking the cell phone, okay? So this means that you'll have some signal there. So then you're going to learn again the model, re-optimize your policy, which then is going to improve and so on. So the model will always stay close to the data that the policy generates, basically. Okay. That's right. So what your colleague said is that the dynamics are accurate, close to the data that we use to train that model. If we plan through the model, or if we sample from it and optimize a policy, which is exactly this, the way of using models, these two ways that we said, then you may land far away from the model's training distribution. And that's why then you need to deploy the predicted actions and update the model accordingly. Okay. Now here is the worst part. So the worst part is the following. If in your initial collected data, your model will not have seen some transitions, correct? And what happens is that if you try to optimize over this model, any transition that is not known will be exploited by the policy. For example, imagine that you never fall off the cliff, then optimizing may say, oh, I think falling off the cliff has very high reward, because you don't know. Do you see? It may as well be super high. So optimizing may lead you to do absolutely crazy things. Now, there are a lot of, does this make sense? So that's precisely the huge problem of model-based reinforcement learning, that for many years, model-based RL could not catch up with model-free reinforcement learning. So let's discuss about this. So what is the challenges in model learning? Well, first of all, the model just can be inaccurate by under-modeling. It's just, if the model class is restrictive, we cannot model all the crazy dynamics, for example, around context and so on. So the other could be that is overfitting, is, as you said, is too expressive, and then far away from the data, it fails. So the model can fail in all different ways, and those errors become worse through unrolling. Okay, it needs to be multimodal to capture different things of the environment, and it can be exploited by the action selection, by this optimization. Whatever the model doesn't know, the optimizer may think that have very high reward. Does this make sense? So this is called model exploitation. The policy exploits the model and results from crazy actions. Yeah, so actually, let me say something more about this. We will see how that model exploitation was solved a couple of years ago. The solution was to model your uncertainty. So if you just train a next state function that is just a regressor or even a classifier of what the next state is, that does not model its uncertainty, when you feed it a state and action that actually doesn't know, it doesn't show in the training set, it may as well map it, as we said, to very high reward. We'll tell you, okay, yeah, jump off the cliff. I haven't seen it. I may as well have very high reward. So optimizing through those models or sampling synthetic experience through those models was not able to lead to policies with good asymptotic performance as training continues. And we'll see how modeling uncertainty in a very simple way was able actually to solve this problem. So this is very, very exciting. Again, modeling your uncertainty here is very, very important. So here is one slide about the objective mismatch in model-based reinforcement learning. I have a paper that I find extremely useful for you to read. I mean, I found it very interesting. Here is the disconnect, guys. Learning models is just a supervised learning problem indeed. You just have a bunch of state action, next state reward, state action, state reward, and you just try to learn the next state function and the reward function. Okay, and you use maximum likelihood. And you want to say, oh, in all the transitions that you saw at training time, make sure you have low error. Now, here comes the policy whose job is to just maximize its reward, right? So it might be very important, the model to be accurate in some parts of the state space and inaccurate in others, because that the policy will not actually prefer that part. Now, this alteration between the policy and the model learning are trying to solve this mismatch. Does this make sense? The fact that, policy is trying to maximize rewards, the model is trying to maximize the likelihood. Now, since you alternate between them, then you push the model more and more towards the data that the policy actually uses. Okay, this is precisely a solution. So you can think of this alteration as trying to fix that objective mismatch. Does this make sense? So what is an ideal curve? The ideal curve is as your model is better, so the model's likelihood go high, then the episodic reward goes high. The resulting policy has highest reward. Do you like this line? Yeah. So here is the actual situation. If you just take a bunch of expert trajectories and train a model and then train your policy, you have this extremely not great plot. Does this make sense? Now, however, if you do this on policy, as we said, so this alteration, then you have this much better behavior, at least around that diagonal. All right. So please check that paper for more details. We are going to have some other fantastic solutions to the problem of mismatch, either on Wednesday or on Monday. Okay. We don't want to have these disjoint objectives. The policy tries to maximize rewards, and the model is just trying to predict any transition in the world. We want to put them together. Okay, that's the idea. Okay. So today's lecture is actually very simple. It's this first case. We have some low-dimensional state, few numbers, and I just want to predict the next state. Okay? Very, very reasonable. You may have your cheetah or your little robot with some joints, and you apply some torque, and then you want to see what's the resulting configuration of your robot, and so on. Next week, we will consider the more challenging case of learning from visual observations. All right? That's it. So we don't have this in today's lecture. Now, two things, though, that you need to remember, because they're insanely important when we learn from visual observations, that the unrolling of the model can either be on the observation state space, which means your model spits out images, and then you feed back the images, or it can be on the latent space, which means here's your observations, and you can concatenate tons of them. Then you jump in the latent space, and your model only needs to predict the dynamics of that latent space. So we call those latent space dynamics models. Okay, and these are the winning models right now. Very, very important. But we just need to worry about model-based RL so far in low-dimensional state space. And here is a picture of what's happening till 2017. Let me show you. The training is starting in that half cheetah. The cheetah's configuration is described by a few numbers. Okay, you train a model-free method and a model-based method, and you see that in the beginning of training, the model-based method is doing much better than the purple, much better than model-free. Then you wait a little bit, and the model-based plateaus, right? And while the model-free goes on and on and on. Okay, so that was the situation. Some very cheap solution, which you don't need to worry, but just to show you the desperation of researchers, was to start with a model-based method and then to continue fine-tuning with model-free method. Okay, so in this way, you are faster in the beginning, and then you also enjoy the good asymptotic performance of model 3. However, now we know what is wrong. We know what was wrong. What was wrong is that we did not estimate our uncertainty. Okay, but in any case, that was the method, very obvious. So we have some experience. We train a dynamics model. We use model predictive control over the model to estimate actions, which means we do look ahead and cross entropy methods, some very simple evolutionary search to estimate actions through the unrolls. And then we deploy those actions, and then we collect new environment transitions that we build a new model and so on. Is this clear, the model-based method? Okay, and the problem, by the way, in general, we're not going to be predicting the next state. We're going to predict the delta S. Okay, so the next state will be the current plus the predicted delta. Okay. Okay, can we skip the model 3 fine-tuning and instead still outperform model 3 methods? And the answer is yes, by representing model's uncertainty. This is a very, very obvious paper. I'll let you go because it's 1:10, but we'll spend 10 minutes to describe it on Wednesday, and is one of your homeworks. I think it's homework 4 for you to implement, to really understand. So hope to please come on Wednesday to finish this and to go into AlphaGo.